Okay, thank you everyone who attended my talk. Let's talk about how to put a lot of logs, efficiently store these logs and query these logs on a single computer. Let's meet. I'm Aliaksandr Valialkin. I'm a software engineer. Primarily, I like writing code in Go because Go is a practical language. It allows writing you pretty efficient code, which is readable and maintainable. And I like writing useful open source software, which works out of the box. This software should work out of the box. That's very important because many open source software developers do not pay much attention to this property of the software. They write software for their own, and they do not think about that the software should work out of the box for the majority of use cases, and that's the problem. And I try solving this problem with the software which I write. I like creating software service which optimize it for speed and low resource usage, and that's why I created VictoriaMetrics database. It's an open source database for metrics. Probably somebody of you already heard about VictoriaMetrics. Have you heard? Yeah, that's good news. And recently I started working on another database specialized for logs. This is VictoriaLogs database. It is also open source, and it is optimized for large amounts of logs. Let's refresh our knowledge about logging. What is logging? The logging is consists of multiple areas. The first area is logs production. Logs usually are produced by servers. These logs may contain some information about what servers do and which requests they process, which errors they encounter, and so on. The typical production logs are generated also by client applications, for example, Android or iPhone applications or desktop applications. There are also logs, popular logs, which are generated by web servers. That's a specialized type of servers. And web servers usually generate so-called access logs. For every incoming request, they store some information, various information for this request in a single log entry. And there are industrial logs which are generated in some industrial manufacturers by some industrial machines and so on. The next step after you produce these logs, they must be collected and stored somewhere, and it is better to store them in a centralized database. This simplifies managing of the stored logs and simplifies searching over all the stored logs. The next step is querying of these stored logs. And important step is archiving old logs. If you require for storing logs for years, for example, because of some law, then you need to take into account this step. Which types of logs do exist? Of course, it's plain text logs, like this in this example. They just, every line represents a single log entry, and it has a plain free form. But if you look closely to every line, you will see that it contains some structure. But this structure isn't fixed, and it can be different across different log lines. And that's why there are structured logs. The difference between unstructured plain text logs and structured logs is that structured logs have a predefined set of fields, log fields, with predefined set of types of values. Like in this example, you can see there are many log fields, and every log field contains some value of given type. And there is a third type of logs, which are named wide events or just events. They are similar to structured logs, but the difference is that such logs may contain hundreds of fields per each log. And the set of these fields per each log type may be different. I recommend you Googling this wide events. What is wide events in asking in Google or ChatGPT, and then you'll get this link and read more about this, what is wide events. And why it is important, because wide events is very good for storing and further analysis of these logs, for further filtering of these logs, for further grouping of these logs by all these different log, hundreds of different log fields. And the more different log fields you add in this wide events, it's better, because it will allow you in the future slice and dice all these collected logs. When logging becomes large scale, probably when you collect a gigabyte of logs per day or terabyte of logs per day, or probably petabyte of logs per day. What do you think? What is the answer? My answer is the following. When logs cannot fit a single computer, then such logs may be named large scale. And this depends on the size of the computer and the database used. For example, if you try storing logs on a Raspberry Pi in Postgres, then it is unlikely that you'll put a lot of logs there, more than a few gigabytes in the best case. So that's large-scale logging for Raspberry Pi logs stored on Postgres. But when we look at another range scale, you can store a petabyte of logs on a single computer with a lot of memory, a lot of disk space, when you use specialized databases for such logs. And how to store a petabyte of logs on a single computer? Any ideas? There are no ideas. Okay. The maximum disk size of a computer is. Let's talk about physical disks. Currently, as I know, the maximum size of physical disk, HDD disk, is around 20 terabytes. And if you use Google Cloud, for example, Google Cloud provides you disks with the sizes up to 64 terabytes. So you can attach 64 terabytes to a single computer in Google Cloud. And this is smaller than 1 petabyte by 16 times. And this means that how we can put this petabyte of logs on a single computer? Probably compress them. If we compress them by more than 16 times, then you can put this petabyte of logs on a single computer with 64 terabytes of disk space. And the good news is that it is achievable, and it works for specialized databases for logs, which can provide you compression rate for real production logs, for example, collected from Kubernetes, with the compression rate up to 50 times and even more. So it is possible to store a petabyte of logs and even more on a single computer if using specialized databases for logs instead of traditional databases such as MySQL or Postgres. And how do this specialized database for logs achieve such high compression ratio for logs? Probably it's magic. No, it's not magic, it's science, computer science. And it's not so hard like it looks at the first time. The first interesting thing which specialized database for logs do is they use column-oriented storage. They store every field in the structured logs into a separate file, and all the values for this field they store it in separate files. And this allows achieving high compression rates for this per field files, because usually every field in logs contain not so similar values or even constant values, which do not change significantly over time, and such values are compressed very well. They can be compressed by hundreds of times. And if you store every log field values into separate files, you can apply specialized codecs for every log field, depending on the type of data stored in this log field. And this type of data can be automatically detected. So, for example, you can use specialized codecs for constants. If the log field contains constant across different logs, then such log field can be compressed by thousands of times. And if this log field contains a small set of values, such as info, error, warning, for example, then it also can be compressed very well by hundreds of times. And this applies also to numbers, timestamps, IP addresses, and so on. How to improve query performance over petabytes of logs? Okay, we stored a petabyte of logs on a single computer, but what about querying speed? Currently, the maximum disk read I/O for SSD disk and NVMe disks doesn't exceed 4 gigabytes per second for high-end NVMe disks. And if we divide 1 petabyte by disk read speed, 5 gigabytes per second, you'll get 70 hours. And this doesn't look like a good number for reading and querying a petabyte of logs. How to improve it? Yeah, we forgot that we compressed this petabyte of logs into 64 terabytes. Then we can divide 64 terabytes by 5 gigabytes per second and get that you need only 4 hours and 27 minutes for reading all these 64 terabytes of data. I hope that you're ready to wait for more than 4 hours for a single query. How to reduce query speed even more? We can skip reading data for unneeded logs. If we store these logs in column-oriented format, as I said before, there is no need to read all the columns. We need to read only the columns which are mentioned in the query, which you are interested in. And in that way, you can reduce the amounts of data which needs to be read from disk and improve query performance. Suppose we have 16 log fields, logs with 16 fields, and every field contains equal amounts of data. And in this case, we can reduce the amounts of data which we can need to read from 64 terabytes only to 4 terabytes. If we need to read only a single field. So the query response time can be reduced by 17 minutes, and that's not so bad, but it can be improved more. If we remember that logs contain a timestamp, and typical queries over logs use filter on this timestamp. You usually analyze logs on some time range. And if we store logs in a format which allows you reading only the data on the given time range, then we can improve performance of such queries. For example, our database contains logs for the last 30 days. And if we need to read only the data on a 3 days time range, for example, for the last 3 days, then we can reduce the amounts of data to read from disk by 10 times, from 4 terabytes to 400 gigabytes. And this improves query performance to 1 minute and 40 seconds. So it's even better. It sounds good for petabyte of logs, but we can improve the speed even more. If we partition logs by the source of these logs, logs are generated by some services or some applications, and if we store logs and group logs received from a single service, instance service or single application, and we store them close to each other physically on disk. And if we query, we know which services we need to query to inspect for logs. In this case, we can use this narrow down the amounts of logs which we need by using special filters on these log streams. For example, if you have 1,000 log streams and only need to read logs from 100 log streams in this database, this can reduce the amounts of data which needs to be read by 10 times again to 40 gigabytes, and this improves query performance to 10 seconds. And 10 seconds is quite good time for queries over petabyte of logs. So if we apply all these techniques mentioned on the previous slides, we can reduce query performance, increase query performance from 70 hours to 10 seconds and for 1 petabyte of logs. And this sounds very good. But we can do even better for a special type of searches, which are used quite frequently in practice. For example, if we need to search for logs, to find logs with some unique or rarely seen string, such as trace ID or IP address or user ID, and so on. And we can improve speed even more for such types of queries. And the answer, the solution for this is named Bloom filters. Anybody knows what is Bloom filters? Only a few people knows that, but let me explain it in a few words. This is a special probabilistic data structure which helps determining whether the given item present in the given set of items. Probably it sounds too difficult to you, but let's check such data structure. For example, if you have 10 items and want to store them in some data block, and want to detect whether item X exists in this data block, then Bloom filter can help you answering this question. The Bloom filter will answer the question whether this item X can exist in this block. But it answers this with some probabilistic it is not exact answer. It exactly answers whether this item doesn't exist in this block. This answer is always exact, but it can answer you that this item exists in this block, but in reality this item will not exist in this block. And Bloom filters need less space, storage space or memory space for storing data for the given items in the set. And probably you already have an idea how to improve query performance for types of queries which need to search for some unique strings across a big number of logs. Yeah, okay, we can split all the logs into word tokens. The word token is just some just regular word in text. And then store this, all these word tokens into Bloom filters. And then we can consult these Bloom filters before reading the actual logs. And since Bloom filters need less space, storage space than actual data for logs, this can improve query performance because you need to read less data for Bloom filters and skip reading data blocks. And for practice, the size of Bloom filters is usually from 10 to 100 times smaller compared to the compressed data for this compressed logs, original logs. And this means that search for the middle in a full stack query performance can be improved by this 10 to 100 times, because you need to read small amounts of data from disk. Let's do some math of the row split for searching, for scanning of logs for some unique trace ID. And this math is simple. You just multiply the disk read speed by the compression ratio of these logs, because they are stored compressed in disk, and multiply by this Bloom filters multiplier, which is 10 to 100 times. And if you do this math, you get that the raw scan speed for such type of queries will be 6.4 terabytes per second on a single computer. So that's pretty impressive number. And okay, we were talking about this specialized databases for logs, and why regular databases for such as Postgres and MySQL do not fit for large-scale logging. Any ideas? Okay. Because regular databases store rows as rows. They store fields in each row close to each other on disk. They do not split these fields into separate files. This is named row-oriented storage. This row-oriented storage is good for searching for all the information about the given row, all the fields for the given row by using indexes. But it is not good for large-scale logging, because it requires you reading all the row fields from disk during queries, even if you need only a single field from these rows. And this also significantly reduces, worsens compression ratio for this data, because if you compress these rows row by row, the usual compression codecs are not so efficient, and you get lower numbers of for compression rate, and increases disk usage. And by default, neither Postgres nor MySQL do not compress data. And also, these typical regular databases store incoming rows as is, one by another, like it receives them, and do not perform any physical grouping of these rows, and do not perform any automatic partitioning. And why this is not good for large amounts of logs? Because it increases the number of hits for even individual rows. For example, you select some logs from big amounts of logs, and this a million of such rows, and these rows are allocated randomly across all the disk space. This means that you need to perform a million mixing reads across different locations of disk space, and this significantly increases the amount of data which needs to be read from disk, because operating systems usually read data in blocks, and the block size is minimum of 4 kilobytes, and for SSDs it's bigger, even bigger. So if you need to read a million of rows located in different locations on the regular database on disk, then you need to read at least 4 gigabytes of data, even if these rows occupy much less space. And also, these traditional databases use B-tree indexes for fast access to the given row on a disk. Such databases excel on quick access to the given individual rows in a table. And typically, the size of these indexes is up to 30% of the size of the data. That's from my experience. And if these indexes do not fit available memory on a computer, then everything becomes very slow. The data ingestion becomes very slow because the database needs to read a lot of additional information from disk for these indexes which do not fit memory. And querying also becomes very slow because it needs to read the same data from disk instead of memory. And computers with terabytes of memory are still rare, and very expensive currently. So it is not a good solution for big amounts of logs. And also databases, typical databases for logs, typical databases such as Postgres and MySQL override the existing data on disk in small chunks. When you update some logs or store some additional new data to disk, it is updated on disk. And B-trees need frequent updates for their nodes during data ingestion, as I said before. And small overrides significantly increase both discrete and write I/O, especially on SSDs and NVMe disks, because such disks usually need to write half megabyte of block per each write on the disk, per each update on the disk. Even if you update only a single byte on the disk. What to do if a single computer cannot handle more logs? You can migrate to specialized databases for logs, which support high amounts of logs. And if you reach scalability limits for a single computer, the next step is to scale horizontally to multiple computers per cluster. And which open source specialized databases for logs exist and which to use. There is Elasticsearch, there is Grafana Loki, there is a ClickHouse, and there is a VictoriaLogs, which I'm working on. Which is better to use? I think you know the answer to this question. Of course, VictoriaLogs, because Elasticsearch needs a ton of memory for large-scale logging. If you run Elasticsearch, you already know this pain. And Grafana Loki is hard to configure and operate properly because it consists of some unclear configuration which constantly breaks with every update and contains a lot of undocumented options. ClickHouse is very good for performance and low resource usage, but it needs very careful tuning of table schema for high performance. And if you do not know how to tune table scheme for your particular use case, then it is likely that ClickHouse will be slow and inefficient for your use case. And VictoriaLogs doesn't need any configuration, doesn't need any table schemes. It works out of the box, accepts all the logs with different log fields, and works very fast and very efficient. Why VictoriaLogs? It's a small advertisement at the end of my talk, because it's open source database optimized for large amounts of logs. It includes all the optimizations which I mentioned on the previous slides, and they work out of the box without any configuration. It can handle hundreds of terabytes of logs per computer in not in theory but in practice. In theory, it can handle more than petabyte of data per computer, but in practice, there are cases when it easily handles hundreds of terabytes of data per computer. And it can scale horizontally to hundreds of computers if you need handling tens of petabytes of logs. It supports all the popular data ingestion protocols for logs, so you don't need change your log shippers, just set the destination for VictoriaLogs and that's it. And as I said, it's very easy to configure and operate. It doesn't need any configuration, and it's schemaless, and it runs efficiently on any hardware, starting from Raspberry Pi and finishing with some beefy computer with hundreds of CPU cores and terabytes of memory. So I recommend you trying VictoriaLogs on your home lab, on Raspberry Pi, or on your home computer. And after you feel that it works great, you can switch your existing log system in production. And here are some reviews from real users of VictoriaLogs. You can find them on the internet. Here is the link. Here is the user who successfully migrated from Elasticsearch to VictoriaLogs. And he was using Elasticsearch cluster with 27 nodes, around 600 CPU cores, and 4.6 terabytes of memory into a single VictoriaLogs instance, single node VictoriaLogs instance, which runs on 8 CPU cores and 64 gigabytes of memory. And he's happy, as you can see. And here's another case when the user wrote a blog post that grabs. Grabbing of logs is a very good thing, and I frequently use grabbing for logs. But the issue with grabbing of logs is that while it is fast and useful, there are better solutions for large amounts of logs. And this user compares regular grabbing with VictoriaLogs on his home laptop, a very old laptop, and concludes that VictoriaLogs is hundreds times faster for typical queries over logs compared to grep. And it uses also less disk space for the ingested logs. Here's another example for users who migrated from Grafana log to VictoriaLogs and reduced their resource usage, memory usage by more than 4 times or 5 times. I don't like this misleading percents when users like that write this percents when they talk about reducing of resource usage, because they are misleading. For example, this 87% means almost 8 times improvement, and 87% it's just misleading. Okay, but this shows TLDR shows that they get query performance increased by almost 20 times when they migrated from Grafana Loki to VictoriaLogs. And also reduced disk space usage by by around 2 times, and so on. So I recommend you join VictoriaMetrics community, VictoriaLogs community, because it's open source, and we are glad to see new users, active users. We have Slack, we have GitHub, we have Mastodon, Reddit, Telegram, and Twitter. And there are some useful links. Here is the VictoriaLogs source code is located by this link. You can just Google it and find. Here is the documentation for VictoriaLogs. And here are links for my social accounts. You can follow me. I regularly publish some insights from my work. And that's it. If you have, we have no time for questions.
Yeah, definitely.
We have time for questions.